Today we will talk about mutual information. The channel, the memoryless channel, which is discrete in nature, that is the inputs are the discrete in nature, that is the symbol, the alphabets that are generating from the source taken at different discrete intervals and given to the channel, and you have the input alphabets, and the channel output will have the output alphabets. And these alphabets are generating at their probabilities, input probability and output probability, and having some transitional probabilities in the channel. This was discussed earlier, and now we are going to talk about what is the mutual information of that channel. So we refresh this discrete memoryless channel having the input and output X and Y, the variables. The channel we have represented, we can represent it, the input alphabets having X, J number of inputs, and Y, K number of inputs. So there are transitional probabilities of YP, YK at Xj. These are all the transitional probabilities in the channel. So at what probability that is getting P of Xj at the input, and we are getting output with the probability of P of Yk. We also come across with a given input probability and transitional probability. So we estimated the output probabilities also. And as well, the entropy average information at the input probability and output probability, so that the average information at the input and output, that is H of X and H of Y, we estimated. If you mention that channel in a matrix form, the transitional probabilities Yk at Xj, see, this is where P of Yk at Xj. So this is where Y0 to X0, for every input of X0, this is the first row for all the outputs. Similarly, for the second input, X1, so these are all the probabilities for all the outputs. So this is what the row indicates for every given input, and this is X0, second row for a given X1 input, and so on. And the output, the probability where the first column referred with output Y0 and second column referred with output Y1 with their transitional probabilities, so on. So this is where we understand in the matrix form, and all the probabilities, sum of all the probabilities is equal to 1. That property must be satisfied. And we can express the output probability as sum of these transitional probabilities and multiplied with their individual probability of the input, and this can be taken as a giant probability, and sum of all these giant probabilities is output probability. So for a j equal to 0 to j minus 1, for all the input j equal to j inputs, so for a given k at the output y and yk, so for every k, output probability can be estimated for all the ranges of input j. Now come to the actual topic of this mutual information of that discrete memoryless channel. As we said that the entropy, the h of x, the average information for a given input probability of p of x. Okay, p of xj. So that is where uncertainty that is observing at the input. So before observing the output. So that is h of x is the uncertainty of the input input before observing the output. So that is where at the input of the channel we observe. If you take H at X, Y given Y, and this is what conditional entropy, we call it as uncertainty of an input of the input channel after observing the channel output. After observing the channel output, whatever the uncertainty at the input channel, that is what conditional entropy H X at Y. So mutual information, the difference between these two while observing the output. So the uncertainty of the input channel while observing the output channel. This is what mutual information. So vice versa, the mutual information. So because the channel is reciprocal, so the X and Y can be reversed as Y and X. So that is what mutual information Y comma X is also uncertainty about the output channel while sending the input while sending the input channel. So this is what I, Y, X. So we can define mutual information as H of X minus H of X at Y. So that is the uncertainty of the input and the uncertainty of input while after observing the output, and difference between these two while observing the output. Similarly, the vice versa. So now, what is the mutual information, if at all we understand based on that given definition? So this is where uh, I understand we can take it as I of X at Y, I X comma Y equal to H of X minus H of X at Y. You know this, H of X as average information of entropy. This is what entropy. So this is where sigma of J for all J, okay, P of Xj logarithmic base to 1 by P of Xj, as you know this. This is already for all J, this is what the entropy. Similarly, the conditional entropy of X at every Y equal to Yk, every output of that Y equal to Yk. So you can take the average that entropy P of Xj at Yk logarithmic base to 1 by P of Xj at Yk for all the range of J, So this is where the conditional entropy for every Y equal to Yk, the similar way for all Y. So that is where the expectation, the mean, average, H at X at Y can be taken sum of all K values. So the output at K values, K number of probabilities we have. So that average we find by multiplying this for every Y equal to Yk, this conditional entropy multiplied with the probability, output probability of Yk, P of Yk. So this is what multiplying with the probability, that is average, that is getting sum of all output K number of values, that you will get the conditional entropy for all X at Y. If you substitute this conditional entropy H X at Y equal to every Yk, so this is what this expression here. So this is where conditional entropy while observing, okay, here, this is what after observing the channel output, that is the conditional entropy, mutual information while observing the channel output. That is what the difference we take. Now, for time being, this is what it is separated and expressed in terms of giant probability. As you know that the h of x is, this is the definition as we just now told, and we are finding out the conditional entropy x at y. So that is where the multiplying with this output probability of hy at y equal to yk for all k. So that is what, this is what sigma k equal to 0 to k minus 1. This is what h x at y equal to yk. P of xj at yk logarithmic base to 1 by xj at yk, and this p of yk is multiplied here and that is being taken. So this is where the this term multiplied with the p of yk of sigma k equal to k minus 1. So this is what becoming this expression. As you know that the product of this p of xj at yk multiplied with p of yk is the giant probability. Giant probability p of xj at yk. This is what giant probability, and that is being substituted here, p of xj at yk multiplied with p of logarithmic base to 1 by p of xj at yk. So as you know that this is what we are substituting as a giant probability by the definition, and the difference between h of x and h of x at y is the mutual information. This minus this. That is what we know, the probabilities, input probabilities, and conditional probability, transitional probability, and giant probability, where the multiplication of these two, that is giving the mutual information here. So this is what the mutual information, the uncertainty about the channel, which is resolved, that is by observing the channel output. So while observing the channel output, we are getting the uncertainty of the channel input is nothing but mutual information. Now, the same, that I of x at comma y is h of x minus h of x at y. This can be taken mutual information because the channel is reciprocal. So I y comma x can be a measure of uncertainty of a channel output while resolving, while sending the channel input. Because the channel input while sending, because y acts as a out input, and y input is a as an output. So that is how that is sending as a channel input while observing the uncertainty about the channel output. So I y comma x equal to h y minus h y at x. So this is what the mutual information in both ways we can consider.